Okay, so what we're going to look at specifically today is something called related rates. So I'll explain what they are first. Then we're going to look at formulas that are related to spheres, because we need to know those formulas in order to do some of our problems. And then we're going to look at two examples of how we use related rates to solve some practical problems. So first of all, I'm going to start off with defining what we mean by related rate. Okay, and I'm going to use different color today for whatever reason. So a related rate, when we say that, in calculus, this is a measurement, okay, that is changing with respect to time so it's a rate, that's why it's called related rates, affecting all the other measurements that are changing in the problem. We'll call it affecting all other measurement changes Okay, so what was an example of this? So, for example, if I had a sphere and I was like a beach ball, and I was blowing up the beach ball by putting air into it, so I was increasing the volume would be growing at a rate, and also the radius would be growing at a different rate. So they're related rates. How much air I put into the beach ball affects how fast the radius grows. Okay, so that would be an example of a related rate. So maybe we'll just type one in. Filling Okay, so filling a beach ball with air increases the volume, and as a result, the radius is changing as well. Okay, so that's basically what we mean by related rates. Okay, when we talk about related rates in calculus, okay, so when we talk about related rates in calculus, we're talking about something changing with respect to time. So when we do differentials, they're called. So if we're changing area, say area, and we want to get the related rate of area, we just go little dA over dt. This represents the change in area with respect to time. Okay, so if you were going to do volume, this could represent volume. So basically, your related rates all have this dt on the bottom. So they're kind of called differentials. Okay, and remember that the derivative of something, it signifies the rate of change at a certain point, or the slope at a certain point. And slope is the rate of change. The rate of change of what depends on what you're taking the derivative of, right? Okay. So we're going to start with the easiest shape to deal with, and that's a circle or a sphere shape. Okay? If you think about volume, surface area, circumference of a sphere, they all have only one measurement, and that's radius, or diameter if you want, but that affects the volume, affects the surface area, affects the circumference. Okay, so there's 3 equations that we have to recall from our grade, 7, 8, 9, 10 days. Okay, circumference. So, circumference is the distance around a circle. That's 2 pi r or pi d, if you remember. This is our radius. This is our circumference. So that's another way to say the perimeter around. And then 2 pi is just a number, right? Okay, and then you also have your surface area. So I'm going to use surface area like that. Okay, that's 4 pi r squared. Still got the same radius. This is surface area. Okay, and then you also have volumes of spheres. Okay, a volume of a sphere is 4/3 pi r cubed. Okay, this is volume. And this is, again, radius. Now, you'll notice something really cool here. Notice the volume and surface area are different derivatives of each other. Right? If you take the derivative of this, right? This 3 would cancel out, you get the surface area. The derivative of volume is the surface area of a sphere, because that's how they're related. So calculus is one of those, once you learn a little bit about the calculus, it kind of makes sense to where all the formulas come from. They come from rates of change and things like that. Okay, and then the other thing we should remember as well, sometimes people use the word diameter rather than radius. Remember that a diameter is just equal to 2 times the radius, because sometimes you'll be talking about that. So we're going to do a related rate on how a volume changes, how a surface area changes, and how our circumference changes with spheres. And we're only going to do spheres today. Okay? And then tomorrow, like I said, won't have a live class because I'll be in Pontex with their gym blast they have there, and we'll be doing some fun stuff, hopefully. And then I'm just going to leave some practice work and dealing with the last couple of days that we've done. And then Friday will probably be a work period as well. Just, we'll do some new stuff on Monday with cones will be our next thing, I think. Okay, so I'm going to do probably a really basic 3-prong example of how you use differentials. So differentials are kind of like doing implicit derivatives, and you still use the derivative rules, but now we're not going to just use y and x like we had before. We're going to be using different variables like volumes and radiuses and all that, but everything's going to be derived with respect to time. So rate of change is something over time, right? So that's why derivatives are used. So a differential, which is what we call these things, is something changing, some measurement changing over time. Okay? So that's what we're going to do. So I'm going to flip the page here, and we're going to do our first sample on this. All right. let's type it in, make it nice and neat. Okay, so let's do the one that I was talking about earlier. Let's say that we're going to be inflating a balloon. So you are inflating a balloon. Now we're going to assume that this is a spherical balloon, so that the radius is increasing, okay, at a rate of 2 centimeters, 2.0 centimeters per second. And this is important. We have to state at what point the radius is. When the balloon has a radius of, let's say, I don't know, 4 centimeters. Period. Find. Okay, we're going to do 3 different finds here. How fast the circumference is growing. We'll go A. How fast the circumference is growing. At that time. Okay. It's going to be all with the same point. Okay. How fast the surface area is growing. And thirdly, the volume. Okay, this is the easiest type we can get. The second one I'm going to do is a little more complex, but this is our simplest one. So the first thing we've got to do is we've got to define our rate that we know. So we've got to define what this is. So the first thing I'm going to do is I'm going to change my marker to a calligraphy pen, and I'm going to turn green, and I'm going to make it skinny. So we're going to define the rate of change, or the given rate. Okay, the radius is increasing at 2 centimeters a second. So dr dt. Okay, that little r is going to be our radius, is 2 centimeters a second. So this is called a differential. Okay, dr dt. Okay, that's our differential for an increasing radius. Okay, if it was decreasing, it would be negative, but it's increasing. Okay, and then this is when r equals 4. Okay. Okay, once we do that, we take the equation of circumference and take the derivative of it with respect to r. So take the circumference equation, that's the first one, 2 pi r, and take the derivative. With respect to r. So this is going to become our dr dt. So we're going to go dc dt equals, now 2 pi is not a variable, it's just a number, so we leave it. This is a variable. The derivative of r is 1, so we're just going to go 1 times dr dt. So dr dt. So now we can find out the rate that the circumference is changing by plugging in our variables. So we take the derivative with respect to r, that's number 2. This is step 1. Step 2. Step 3 is we plug the variables in. And solve for dc dt. Okay, so this would be dc dt equals 2 pi times 2 centimeters a second. So our final answer is dc dt equals 4 pi centimeters per second. Or if you don't like pi, you could multiply that by 3.14 and get whatever it is, 12 point whatever it is. I just usually leave it as 4 pi. But 4 pi is 12.56. So that's how fast the circumference is growing. So the radius is growing by 2 centimeters a second, and the circumference is growing by 12.56 centimeters a second. Okay, pretty easy, right? Same pattern for surface area, except we change the formula. Okay, same idea. Okay, I'll do this one in a different color. Let's use red. Okay, the surface area formula for a sphere, we'll write that out. Surface area equals 4 pi r squared. So this is a little bit more challenging. Okay, we still have the same, this is still the facts here, right? But now we're going to do the derivative with respect to r. So dsa for surface area over dt equals, okay, 4 pi is just a number. Okay, pi is a number, it's not a variable, so there's no derivative there. So 4 pi, take the 2 out front, times 2r, okay, because there's still an r there. And then we have to add the dr dt. Okay, just like this one was a 1, but we still have to multiply it by dr dt to get the related rate. Okay, so then we can simplify. This is going to be 8 pi r dr dt. Okay, now we're into plugging the variables. Now we have to use 4 centimeters in our variable as well. And you'll notice that the variables will work out. Surface area should be in centimeters squared per second. Okay, so we're going to go 8 pi times 4 centimeters times 2 centimeters a second. And that's going to give us our result. Okay, so 8 pi, okay, so we got 2 times 4 is 8. 8 times 8 is 64. So we got 64 pi centimeters squared per second. Okay, and that's the rate of change of the surface area. Now, if we wanted to do that one in decimals, you can just go 64. Where's my pi button on my calculator here? 64. So it's about 201 centimeters squared per second. Okay? So pretty easy to do. Okay, this really makes it quite easy when we're just having one variable. Okay, when we get into cones, it's a little bit more difficult, but this is our first one, which we won't do till Monday probably. Okay, and our third one is volume. Okay, so let's slide this up just a sliver. We'll go into blue, and we'll do volume now. Okay, so volume is 4/3 pi r cubed. Okay, we still have those same inputs for dr dt and 4 centimeters for r for radius. Okay, so we're going to take the derivative. So this is dv dt with respect to time. dv dt. Okay, 4/3 pi is just a number. Okay, and then we got to go take the derivative of r. So 3r squared times 3r squared, and then we got to times that by dr dt. Okay, we can do a little bit of simplifying here to make it a little bit easier on ourselves. This 3 times that 4 is 12 divided by that 3 would get us back to 4. And look what it turns into. 4 pi r squared dr dt. It's really weird. Okay, so now we're going to plug our numbers, and remember that volume should be in centimeters cubed per second. So when we plug our numbers in, we keep our units. So we got 4 pi times 4 centimeters squared times dr dt, which was 2 centimeters per second. Okay, so this is 16. 16 times 4 times 2. 16 times 4 times 2 is 128 pi centimeters cubed per second. Or, if you like, using 3.14, that's about 402 centimeters cubed per second. Okay, so pretty straightforward. Where it gets a little more challenging is if I give you the rate of change of a surface area. So you have to convert it down to the rate of change of the radius so that you can plug it into the other one. So if I say the surface area is changing by this much, how much is the volume changing by? They're both related by radius. You use one to find the dr dt and plug it into the other. So we'll do one example like that, and that'll be it for today. And then tomorrow, I will pop up some practice questions on maybe spheres, maybe some of the distance problems that we had in the past, so that you can work on that. And we'll work on it tomorrow and Friday. Some of my students won't be here. I won't be here. Some of us we're going to be going to something in Ponix, so we'll be there. Some of you guys will be there as well. So that means that that'll be just a work period, and then Friday will just be a work period on practicing some stuff. I will be online on Friday, though, in case there's questions. Okay? And that's kind of how we're going to go this week. All right, let's do our second example, the one that would be have a little more complexity to it. Not a lot more, but a little more. Okay, we'll flip ahead. Let me dig out my little example here. All right, so let's say that a beach ball, I'm going to use a beach ball this time instead of a balloon. And to think, when I was a boy, this is how old I am, my school didn't even offer calculus. I didn't learn calculus till I was in university level. Fairly useful. A beach ball is being inflated at, let's say, 20 centimeters per second, growing its circumference. So we're not talking about radius, we're talking about circumference, okay? The beach ball is inflated at 20 centimeters per second, growing its circumference when the diameter, so I'm going to try to trick you, is 30 centimeters. Okay, so that means the radius is 15, okay? So don't get confused. How is the volume of the beach ball changing with time? Well, I could have said surface area, but I'm going to go volume. Okay, so one of the things you have to be aware of and be careful of is that you don't get trapped on plugging the diameter in when it's supposed to be radius or something. I sometimes do that, so you have to be careful. Keep a peeled eye on me a little bit. Okay, so the first thing we know, we're going to define that we know that dc dt is 20 centimeters a second. Okay, and we know that we want to get volume but the thing that relates volume is not dc dt, it's dr dt. So we have to use the circumference formula to solve for dr dt. Okay, so let's go ahead and do that. So dc dt equals 2 pi r, derivative of r is 1 times dr dt. Okay, so this is 20 centimeters a second equals 2 pi dr dt. Okay, so we're going to divide both sides by 2 pi. Okay, let's see what we get. Okay, 2 pi divided by, or no, 20, sorry, divided by 2 pi. Okay, 3.18. Okay, and our units are still, there's no units to cancel out here or anything, so it's still centimeters per second. Okay, so that's our related rate for the radius. So now we can go ahead and either work on our surface area or our volume, whatever the question's asking us to work on. If it started with surface area, it would have been different a little bit, depending on where it starts. So we're going to do volume because that's what it's asking. Okay, so we're going to do dv dt. That's what we want. Okay, dv dt. Okay, taking that derivative, 4 thirds pi times 3r squared. Okay, for that r derivative times dr dt. at least with the spheres, you'll find it very easy to work through, and you kind of get the same answer when you're doing the derivative. Other problems that we do later on will have more complex formulas, and the derivatives might be slightly different, okay? Cones especially. Okay, so let's simplify. dv dt equals 4 pi r squared dr dt. Okay, now we know we calculated dr dt right here. We have a diameter right there, so that means little r equals 15 centimeters. Okay, so at that, when the diameter, so we want to make sure, because we have little r in there, we have to make sure that it's appropriate unit, or sorry, the appropriate measurement. Okay, so this dv dt, which we're trying to find, would be 4 pi times 15 centimeters squared, okay, times the number that we got here, 3.18 centimeters a second. Okay, then we get our calculator out and we're going to do some crunching of numbers. Okay, since we got decimals over here, we might as well change that pi into a decimal as well. And then you're going to get cubic centimeters per second, because you got a squared centimeter times a centimeter per second. Okay, so let's go. 15 squared, that is 225 times 4 pi times 3.18. So I get 8,991. So 8,991 cubic centimeters per second. Now, you could probably just say 9,000, depending on how significant your measurements are, right? For doing two significant figures, you'd probably just round it to 9,000, because that would, round it to that one there. Okay? So this is your dv dt. All right, spheres. Those are the two main kinds of problems. The other one that I might have thrown in there is surface area. Okay, the one problem is starting from getting the radius change is always key with spheres, because the radius change is always what's driving the change of volume, the change of surface area, or the change of perimeter or circumference. Okay? Any questions on those two examples? I'm going to show you a couple things here, and then I'm going to let you guys go in about 5 minutes here. Okay, so that's our instructional part for today. So what I'm going to do is I'm going to pop up for Thursday and Friday some practice. Okay, now I won't be live. I will be live Friday. Okay, I'll be riding a bus. Probably on Thursday, coming back. Okay, so I'll be live here. So if there's questions, and we're going to work on, there's two, I'm going to put in practice with distance problems, and I'll show you what they look like. I already posted them. And then I will put in as well practice with spheres. I have not put those up, but I'll put those up before I go anywhere tomorrow. Okay, so let me show you. And of course, I'm assuming that everybody's busy and they got things to do with grad and they got all kinds of stuff. So you're not going to sit there and do hundreds and hundreds of calculus problems, probably, unless you really like it. So you're going to just do some of them, not all of them, right? Okay, so let me show you. Let me get my, where am I here? I got to get to my, I'll just bring a new one over here. Let me just show you what I'm talking about. All right, so let's go into our classroom here. Okay. So I have not put up, but I'll show you where they are when I do what they look like. Okay, so here we are. We're just motoring along pretty good. We're about halfway through related rates. Okay, and I've got some distance problems that were based on day 4 lecture. So here I've got the problems, and these ones have the diagram. Okay, there's 6 of them. Don't do all 6 unless you really enjoy these. Do a few of them. Do 3 of them or so. Okay, and then the solutions for that are written uglily. I don't know how to say that word. Ugly. I don't know. Ugly. Lily. I don't know. You guys figured it out. By me. So here's the solutions. Okay. Now, the other one that I have, and I'll show you here, I have to go in a different spot here, that I haven't posted yet, but it looks like this. Where is it here? There it is. So this will be your sphere problems, and these ones are fairly old. Yeah, these are. So if you look at kind of this will give you an idea what we got left. So here's what we're working on. Okay, so we're in here, and we've got this little bit here and all these practice ones here. So sphere practice, there's the related rates practice day 6. Looks like this. Okay, so I've got 4 there and 4 bonus questions. Just don't worry about the bonus ones as much as these ones, and then I'll post them up. So that'll be Thursday, Friday. Okay. Any questions for me then from you guys? Where's my... Here, I got to get back to where I was. I got so many things open here. Oh boy. All right, there we go. Okay, so any particular questions that anybody has? Okay, remember, okay, there's still a few people that need to do their curves yet, their curve sketches and stuff. Okay, so most of the ones that I've got, I've corrected and sent back already, so work through that as well. But other than that, I'm going to let you guys go today, and we'll be working on those things next day, and have a good, hopefully it's nice and warm, and we'll talk to you guys on, not tomorrow, but on Friday. We'll see you Friday. Any questions from you, Dave? Everything's going okay?
Yeah.
Okay.
All right.
Okay. If you get stuck, just ask.
Okay. Okay, I'm trying to...
My prep period's prep period too, but if you come, like if you're coming to do supervision or something, just let me know ahead of time and I'll just stay.
Oh, okay, sure.
And make sure that if you have questions,
Okay, appreciate it.
if you get stuck or whatever.
I am juggling a lot of things right now.
Yeah, because it's grad and everything else is